Hello and welcome. This is the first of a series of lectures on number sequences and the various methods we employ to find patterns in them and express them as algebraic statements. We are going to be looking at some basic sequences, then we are going to move to some advanced ones. We are going to employ what is known as heuristics or problem-solving techniques. While many techniques exist, in an examination only a few options are available to you. That is why we are going to be spending a lot of time going through those techniques which are going to aid you in an examination in a very limited time. Now a sequence may be given to you like the one on your screen, 0, 1, 3, 6, 10, 15, but doesn't end here, and you put 3 dots after 15 to indicate that this sequence continues infinitely. We notice that every entry into the sequence can be numbered. For example, the first entry is 0, the second one is 1, third one is 3, fourth one is 6, and so on. This makes it very easier for us to find something called the nth term. The nth term is the underlying law that governs the numbers of the sequence. For example, if you are to produce the 7th number, you are to identify that law that caused the sequence to grow from 0 to 1, 1 to 3, 3 to 6, 6 to 10, and 10 to 15. Now the nth term can be expressed in 2 ways. The first one is cognitively and the other one is algebraically. In cognitively, you just study the sequence, you find a general rule, and you find the next few numbers or entries in the sequence. And you know them to be true because you have correctly identified how to progress from 0 to 1, 1 to 3, and 3 to 6. Let me show you. Here I can identify that every number differs by a certain amount. However, that amount is increasing as we go further in the sequence. For example, the difference between 0 and 1 is 1, between 1 and 3 is 2, 3 and 6 is 3, 6 and 10 is 4, 10 and 15 is 5. So what will be the difference between the 6th term, that is n is equal to 6, and the 7th term, this one here? Yes, 15 plus 6. And so we will get 21. So if we try and find number 8, that is 28. So this is cognitive. We have learned through our skills in identifying patterns how to get to the next term. Algebraically, however, that is more tricky because now you have to write an algebraic expression that is going to take n as the input and output the sequence. For example, if I put n is equal to 5 in it, it should give me 10. And if I put n is equal to 8 in it, it should give me 28. So how do we find the algebraic expression? Let me clear the space and write the sequence again. Let's study the numbers in the sequence more closely. 0 can be written as 1 minus 1, 1 can be written as 2 minus 1, but 3 cannot be written as 3 minus 1. Oh, let's keep going. Now where the numbers exactly don't add up, let's add something. Look at n is equal to 3. 3 minus 1 is 2. If you add 1, it becomes 3. n is equal to 4. 4 minus 1 is 3. If you add 3, it becomes 6. Next one, 5 minus 1 is 4. If you add 6, it becomes 10. Now, here is the pattern. In 2 minus 1, you are to add plus 0, and in 1 minus 1, you have to add plus 0 again. But the pattern is that this is actually the value of the sequence at the previous value of n. So, this 1 minus 1, 2 minus 1, 3 minus 1 can be written as n minus 1. However, the number that we add after it is actually the previous term. And our sequence should be only in terms of n. We can't ask the previous value of the sequence to be recorded and add it to our new value. So while it makes cognitive sense, we can't actually use this. So we have to find some other way to find an expression for the sequence. Now let's write the value of n minus 1 beneath the value of n. Now let's find a link between n minus 1 and the value of the sequence. Here we are. If you multiply n minus 1 by a different number every time, we get the original sequence. 0, 1, 3, 6, 10, 15, 21, and 28. So what's the link between these numbers here and n here? We have found one part of the pattern, that is n minus 1. but we're not sure if it really is a part of the pattern. Why? Because it just sprang out of nowhere. There's no reason to have n-1. It could have been n-3, n-4, n-10. So, if we find an expression that connects this part to this part, then our assumption of n-1 will be validated. Now notice something. Starting from the right, you can see that this portion here, they are all actually n divided by 2. 4 is 8 divided by 2, 3.5 is 7 divided by 2, 3 is 6 divided by 2, 2.5 is 5 divided by 2, and 2 is 4 divided by 2, 1.5 is 3 divided by 2, 1 is 2 divided by 2, but we have a problem here. This one. What do we put here? We have 1 here. So why don't we put something else? Because anything multiplied by 0 gives 0, so why do we have 1 here? Let me change that. Here, I've put 0.5 over there, and so this becomes 1 divided by 2. Now, what is this sequence? This is n divided by 2. All of these. And what is its link with this one? The link is that you multiply them together, like we've done here. And you get the value of the sequence. So our assumption is valid. Our nth term is n by 2 multiplied by n-1. If you place any of these values in it, you will get the nth term. For example, if you place 8 inside of it, you will get 28 as expected. So this confirms that our nth term expression was correct. So now you see that it's very easy to find the cognitive expression for the sequence. In your head you can find the pattern, but to find the algebraic expression it's pretty hard. And we are going to be linking the two methods together so that you can find the nth term for any sequence. The next video is in the description of this one. You can click on the link after this video is finished. If you have any questions, please ask them in the comments section. I'll be very happy to answer them. Thank you for watching.